Okay, 11.6. So this is a chapter with a couple ideas in it. Absolute convergence, ratio test, root test. It's kind of a random bundle, but these guys are conceptually connected, so they kind of make sense to be together. A series is called absolutely convergent, so this is our first chapter heading title. A series is absolutely convergent if the sum of the magnitudes is convergent. It's saying, if you think about it, you have, a piece of string, and it goes, and maybe it's 2, but you chop the string up, and then into smaller pieces, and then you move the pieces around, head to tail, like vector addition. So if you have, what do we have? We had like 1, 1/2, 1/4, and 1/8. If these little pieces all go to 2, but then you take them and you move them around and you say, okay, well, I'm going to go backwards sometimes. I'm going to go like that. I'm going to go this way. I'm going to go backwards every so often. Well, if your original piece of string didn't go very far, then making the string go backwards sometimes isn't going to cause you to go to infinity. It's kind of intuitive if you think about it. It's pretty obvious. This is in 2D. The same thing works in 3D. We're usually like, we're just doing plus and minus. We're in 1D. 2D, think about complex numbers. Or 3D, you can think about 3D, just 3D, right? Your magnitude could be in 3 dimensions. This whole thing will still work. So we're saying, of all these guys, if you moved all these arrows around and made them all go in the same direction, and they did not go off to infinity, then when you move them around, then they still can't. I can draw this same picture whether or not, just this. I can draw this picture anytime the magnitude of the terms is reaching a limit. But I want you to know this means something even stronger than what the picture looks like. I'm just drawing a little bundle, sort of indicating that everybody is bounded. But this really is stronger. What I'm saying. I'm saying if you take them all and line them up in the same direction, if they go to a limit, then you can allow the magnitudes to come back into play, and they can't possibly mess up the convergence. It can change the convergence, obviously. It'll be convergent to somewhere else, but it will still be convergent. All right, so ratio test. Ratio test is something important. And we're saying it looks kind of like the limit comparison test, but the limit comparison test, you had like BNs up here, and you were comparing 2 series to each other. The ratio test, you're kind of comparing yourself to yourself. You're looking as you march along from term to term to term. Are you going to some limit, and the limit has to be less than 1. Well, why? So you want to make sure that there's some kind of common ratio. We're looking for something of this format. Okay, we're looking for that, and we're searching specifically for R. This is the whole goal. We're looking at some way of extracting an R. But it doesn't have to be like strictly a geometric series. But we're going to look for a generic R, meaning as long as we're going there in the limit, that's all we really worry about. We're not worried about, we could be a hair over or a hair under, it doesn't matter. As long as we kind of have a common ratio, then we're okay. And furthermore, if this limit is 0, that tells you your common ratio essentially keeps shrinking down to 0. And that's okay too, because if your common ratio is anything less than 1, it's fine. So some things converge even faster. Okay. Okay, what other convergent series do we know? So let's just think about this for a second. So can we use this? The question is, can we use this tool on something we already know that isn't a geometric series? Let's see. What happens here is, unfortunately, we're not going to be able to use it. So let's look. This successive ratio is, well, let's see. It's not 1/2, right? If you go from here to here, you multiply by 2 squared over 3 squared, unfortunately. So what happens from 1 over 9 to 1 over 16? Well, we have to multiply by 3 squared over 4 squared. And then as you go from piece to piece, this guy goes to a ratio of 1. And you're like, well, that's no good. Well, all this is telling you is that you can't use this tool to show that this series converges. There's lots of other tools you can use, but not this one. And specifically, this should remind you that this powerful tool is completely useless on any kind of p-series, because p-series this is a type of p-series. This is p-series, p equals 2, right? Over here, the 2. But if p equals 1, we know that thing diverges. If p is greater than 1, it converges. And we have tools to do that, but this isn't that tool. So not every tool works for every type of problem. Okay? Alright, let's take yet another look at the geometric series. If you take the nth root of each term, let's not look at the first term, I don't like that. But the nth root of everything else, you just get r. And so the root test is just another way to see if you essentially are looking at a geometric series. So there's some things that just look like, you know, if you have a sequence that looks like this or whatever, you have, that's no good, right? That limit is going to be 5. That would be bad. But if you do something like 1 plus 1 over n to the n, oh, well, that's okay, because those innards are going to something. No, that's actually, that's not gonna work either. Whoops, sorry. What if we say 1/2 plus 1 over n to the n? Will that work by the root test? That's okay. If I take the nth root of this goes to a limit as n goes to infinity, and that is less than 1. Okay, so this guy converges by the root test. Now, it doesn't necessarily mean that, for example, like we know this guy actually wasn't going to converge anyway, but what about this other guy? Okay, maybe he converged, but the root test isn't going to show you that. So in this case, the root test will tell you that, you know, this particular 1/2 plus 1 over n, that thing is going to 1/2 inside as you take the nth root of all those pieces. So, I mean, that one will converge. Okay, so again, not every tool is made for every series, and your homework actually tests that very thoroughly, and actually a very sneaky homework at that, and you've noticed that by now. Right, so if you get L equal 1, it's inconclusive. We know this guy converges, right? But this is not the tool that helps us see that. Alright. So, sorry, I've got all these pieces. I only want to show you one at a time. I'm not really sure how to do that. Okay. Okay. What if you have a limit of the terms where you go limit, you know, a n plus 1. This is not letting me control it. There we go. Sorry, try not to peek too much. I'll put these up together. Okay. If a n plus 1 is on top instead of on bottom, and you know, and you're going to 8, this means you're diverging. And so I can just take the formula and tweak it a teeny little bit. It looks the same. Okay, right? This guy just visually looks the same as this guy, but you should train your eye to see what's actually going on, what's actually being said, and don't just look at it as something to memorize, like, oh, I have to memorize these rules. You should see this first one here, this guy here, and you should say, okay, the terms are getting bigger and bigger and bigger, And if the terms are getting bigger and bigger and bigger, it's definitely diverging. I mean, that's ick. That's disgusting. I mean, even if we're going to plus and minus 1, it might just go plus and minus 1 over the origin, but it's not going to. What if we flip this guy, though? This, if we flip it, then we have a common ratio of 1/8. So you should be able to look at these and see what is actually being said, and then from that extract the truth. Okay, what about this next example over here? Is this alternating? Is this divergent, conditional convergent, or absolute convergent? We haven't really talked about that too much. So I just want to know if we have conditional convergence, not absolute convergence. This is absolute convergence. No, so this is just like 1 over n, but the alternating harmonic series is conditionally convergent, so you would call this one conditionally convergent. It's not it's not divergent. You would just classify it the same way you would the alternating harmonic series. So when you see something and you say, well, you know what, n over n squared is just 1 over n, that 4 isn't really going to do anything, just say, okay, it's exactly like 1 over n. They're just hiding it a little tiny bit. They're not even doing much work to hide it, but they're hiding it. Okay, next question down here. What's going on? Okay, so you're thinking it's probably going to be that the 5s are going to win out. You know, the 5 to the n. After you've done several of these, you just get, in your mind, you have a sort of a roadmap of what's more powerful and what's less powerful, and I gave you that in class. Let's see if I can remember exactly which ones I gave you. So if I can find a little piece of space here. So, you know what? Okay, let me see, because I couldn't find a piece of space to write on. But if you have, you know, your polynomials n squared, n cubed, obviously the higher polynomial is the more, the faster something grows. But then you get into things like, you know, 2 to the n is slower than 3 to the n, is slower than 10 to the n, obviously those things. And then you have something like n factorial, and then you have n to the n, and these are faster. They all go to infinity. But then you have natural log of n down here, natural log of n, okay? So there's other things in here, but this is the basic lineup. And then you have something like in here you have square root of n. That's just n to the 1/2, so that's just, you know, one of the p series. Can I crank that p down so low that I can get into the natural log zone? No, I can't. But you should also be aware, for example, n, this is a bad looking n versus n natural log of n. Well, natural log of n is faster than n, but it's certainly nowhere near as fast as n squared. Having an actual, you know, natural log of n in there is only going to hike you up a teeny bit. You're going to look pretty much like an n to that n squared. That's kind of what's going to happen. Okay, so I think we're back on page 17 or something. Okay. Oh yeah, we were. But then you can just use this test, your an plus 1 over an. You're looking for a common ratio, and you can see what happens. That over time, the n plus 1 over n, these guys just cancel out. Nobody cares about those. So it just looks like 1 over 5. And so your intuition is proven right by this tool. So as you use these tools, you build more and more intuition, and then the intuition stays with you. And then when you see a problem, you just instinctively know what to do, and then you have to kind of scrounge around and say, okay, what tool can I use to prove that this is right? Because I know this is right, but I just have to look for a tool that'll do that. And very often, more than one tool will give you the answer you're looking for. Okay, so in this case we have a p-series fighting against a polynomial, and the polynomial will it will lose actually, because p-series is more important. It grows faster than a polynomial. It just doesn't look like it, you know. So even this 1.0001 over n to the 9999, it's not going to actually be different. Sorry, I need an n up here. This is essentially the same animal that we're looking at. It just looks terribly different. But they'll both either converge or they're both diverge. And then what actually happens is you have this lovely situation. Again, the n to the fourth, we don't care. N plus 1 to the fourth or n to the fourth, it's the same. And then you get rid of n copies of 1.1, so 1.1 to the n disappears in both. And it's just like, what? You're like, that 1.1 looks so innocent. But it's interest. It's very, very slow growing interest, but it's exponential growth. So it takes much longer to get started. The 1.0001 to the n takes longer to get started than n to the 9999. But it's going to have this kind of growth. It's going to look like, let's see, it's going to be really small, 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 and all of a sudden it's going to shoot up. Okay, it's just going to go. That n to the 9999 is going to squish that thing down for a very long time, but once it stops being effective, then the exponential growth is just going to take over. So that guy diverges. Okay, we need a flashback, but from what you said in class, a lot of you did not hear this before. So this is famous. This guy is going to be E. Okay, so that's the big secret. That guy goes to E, but that's important to know. But there's a certain kind of, well, we did this in the first week of class, but it's in with the L'Hopital's rule stuff. Okay, so rather than actually just finding the limit, we actually have to take the natural log of both sides. Otherwise, this isn't going to work. We have a special rule that says if this limit actually is well defined, if we decide to take the natural log of both sides, that we can actually switch the limit and the natural log, and then this n just comes out because, I mean, that happens, right? That's no big surprise, because that was the whole reason we wanted to do that. We wanted that n to jump down in front of the natural log, okay? But the big thing is you can switch the order of the natural log and the limit, provided everything's cool and everything's working. We still have a problem though. We have infinity times 0. What we have here, this guy's going to infinity, natural log of 1 is 0, so we have infinity times 0, so that's indeterminate. So we have to stack these guys. So we turn n into 1 over n. The other option we have is we could do natural log. We could turn this into 1 over natural log of this stuff, but it just seems like more mess to do that. And so we just turn n into 1 over n and stick it on the bottom. And so instead of having infinity times 0, we have a stacked 0 over 0. Okay? And then we can use L'Hopital's rule. We just use it once or twice, I forget. I guess once works, and then you work all this stuff out, and then this limit goes to 1, and you think, okay, the limit's 1. It's like, no, remember we took the natural log of both sides. And then you say, aha, 1 is the natural log of L, so then you take e to the power of both sides. This is to undo our setup step. Okay, so up here we did this setup. Okay, we did this setup step. So now we have to undo it down here. And then that makes sense. Okay, that limit has to go to e. Okay, so flashback is over. We go on to the next problem with the knowledge that we can do that limit in a snap as soon as we see it. Okay. Test the convergence of the following sum using the ratio test. Okay, well, actually, because of that list, I told you n to the n wins out over n factorial. So this should be straightforward to prove. It is. But having that tool in our back pocket, knowing that the limit of 1 plus 1 over n all to the n, that stuff equals e, that's just going to get us out of our jam faster, that's all. Okay, so if I take this rule, an plus 1 over an, take the absolute values, stack them all up, do the algebra, then we go directly to this expression, which we already know goes to E. But E is less than infinity, it's a limit, and that's, unfortunately, it's less than infinity, but we're looking at the ratio, right? You were looking at, I should say, the important thing is, who cares if it's less than infinity? What I meant to say is it's greater than 1, so we're unhappy. I think I was so excited to see E that in my notes I put a happy face, but we're actually unhappy to see E because that means we're greater than 1 and we're top heavy, we're multiplying by E in each successive term. So we're just divergent. And I made up this silly term called absolutely divergent. It's my own made up word. It doesn't mean anything. I'm just being silly. Okay?